So now we have our first example. The probability of me winning a game of squash against, and I don't really want to use an annoying student's name, so let's just call this person Bob, is 0.8. What is the probability that I'll win 3 of the next 4 games? And then determine the probability distribution for X, i.e. the number of wins for Mr. Manson over the next 4 games. Now, I could draw a tree diagram for this, but I want an easier way, because I've just done a tree diagram for a 3 event system and it was already out of hand. This is now a 4 event system, which means I have to add an extra event onto this. So I really want to avoid that. So what I'm going to do instead is go back up to here and recognize that there is a pattern emerging. There is a 1-way, 3 ways, 3 ways, 1-way pattern emerging. And there's also a pattern emerging here. That's p cubed. That's p squared times q, that's p times q squared, and that's q cubed. So let's go down and have a look at a summary of this pattern and then use it for example 1. Here is example 1, but in the general form. So we can be more efficient. We have event 1, 2, 3, and 4. In this case, I'll bring this back to the squash example. If I stretch this out and have a look at the number of successes, I can see there is one way of getting 4 successes, so I'll put a 1 in there, and in orange there are 4 ways of getting 3 successes, so I'll put a 4 in here, and in green there is 6 ways of getting 2 successes, and then in light blue there are 4 ways of getting 1 success, and then finally in purple there's 1 way of getting no successes, 4 failures. And the probability is, well, the probability of 4 successes is equal to the probability of success, so I'll just do this in pink, the same color, multiplied by itself 4 times. So this is equal to 1 times p to the power of 4. And remember, we defined earlier that p is our probability of success. And the probability of 3 successes is success times success times success times failure. So that means that we've got 4 ways of doing it. P will happen 3 times and Q will occur once. And then in green, the probability of 2 successes, there are 6 ways of doing it. P squared for the 2 successes and Q squared for the 2 failures. And then we have light blue, the probability of 1 success, 4 ways of doing it. P to the power of 1, which is just P, times Q cubed, because we have 3 failures. And then lastly, there is 1 way of getting no successes, and we just multiply that by 4 failures, so Q to the power of 4. This is actually a really good representation of our generalization. And if I was to write this out a little bit neater and a bit clearer, I just get P to the power of 4, then I get 4pq, and the P is cubed, and I get 6p squared q squared, 4pq cubed, and then q to the power of 4. And this is a generalization of the Bernoulli distribution, the overall table of probabilities that we get. So if I was to bring this back up into our example, I could easily define that P is equal to 0.8, that's stated here, and that tells me that Q is equal to 0.2 because P plus Q must be complementary, they must add to give 1. What is the probability that I'll win 3 of the next 4 games? Well, that of course will be equal to the probability that X equals 3 will be 4 times P to the power of 3 times Q to the power of 1. I've just got this straight out of this table. And that will be equal to 4 times 0.8 cubed times 0.2, and that will be equal to 0.4096. And I can use the same information to determine my probability distribution. And so I'll do that quickly now. Okay, there's my probability distribution, and you can see that the most likely outcomes are 4 and 3, which makes sense because I've got a much stronger game than Bob, and I've got an 80% chance of winning, so you'd expect me to win 3 or 4 of the games overall. 2's possible, 1 and 0 seem quite unlikely, but you know, it might still happen. So there's how we can use our idea of binomial probabilities and Bernoulli distributions with a nice generalization on Pascal's triangle to develop our probabilities. And there's our overall distribution. So here's some standard ones, and we've just seen 4 events here, and the 4 events come out as p to the power 4, 4p cubed, q, etc., etc. But you'll notice here, firstly, these numbers popping up, which I've just mentioned, and these are directly from Pascal's triangle. And there's 1, 4, 6, 5, 4, 1. And so you could write down a 5% system just based purely on your knowledge of Pascal's triangle. And so you've talked previously about using combinatorics to build that expansion, binomial expansion, but we can use that in binomial probability as well. As you can see here, for an n-event system, the probabilities can be calculated for no successes. It's nc0, so that's a bit misplaced, p to the power 0, q to the power of n. And then for one event, we have nc1, p to the power of 1, n minus q to the power of n minus 1. So you see this is, if we want 0 successes, we get our probability of success to the power of 0, but we get our probability of failure to the full amount. And then we get 1 minus, so the full amount minus 1 failures for a 1 event system, 1 and 1 match there. 2 and 2, n minus 2. X and, my apologies, x and n minus x, and this is p to the power of x. And that leads us to this generalization here. The probability that x equals x, so that the overall system equals one particular point, is ncx times p to the power of x times q to the power of n minus x. And you might see q written as 1 minus p, you might see x written as k. There's a variety of different ways that can be represented, but this is ultimately it. Additionally, here in pink and brown, you'll see that p plus q to the power of n equals this expansion. That's how binomial expansion work. And p plus q add to give 1. So that expansion equals 1, and all probabilities add up to 1, which is a really nice result and brings the whole topic in together, and something for you to think about. And we also have this notation. So we've seen this previously as well, but NCR can also be written as NCR like that, and it can also be written as N and R inside tall brackets. So just be wary of any of those notations.